Ship one binary that compiles different code on Linux and Windows. Bake your entire web frontend HTML, CSS templates inside the executable so deployment is copying a single file. Develop 5 interdependent modules at once without ever touching a go.mod. These are 3 features of the Go toolchain that change how you build and ship software: build tags, file embedding, and workspace mode. This episode covers all 3, how they work, when to use them, and the traps to avoid. A build tag is a comment at the top of a Go file, before the package declaration, that controls whether the file is included in the build. If the constraint matches the current build configuration, the file compiles. If it doesn't, the compiler behaves as if the file doesn't exist. The modern format, introduced in Go 1.17, is // go, build followed by an expression. You'll still see the older // plus build comment in existing code. It's supported for compatibility, but write new code with the Go build form. Constraints can test the operating system Linux, Darwin, Windows, the architecture AMD 64, ARM 64, WASM, the Go version, Go 1.18 and up, and any custom tag you define yourself. The expressions are real Boolean logic. $for and $pipe for, or exclamation mark for not, and parentheses for grouping. So Linux and an AMD 64 means Linux on AMD 64 only. Linux Darwin and an 386 means Linux or Mac OS, but not on 32-bit x86. And Go 1.18 means Go 1.18 or newer. Version tags are cumulative. The most common use of build tags is one file per platform. You define the same function, same name, same signature, in 2 files, one tagged Unix, one tagged Windows. Go's build system selects the right file automatically. The rest of your code just calls the function and never knows there are multiple implementations. 3 rules make this work. First, files whose tags don't match are silently excluded, no error, no warning, they're just not there. Second, the function signature must be identical across every variant, because exactly one of them will be compiled into any given build. Third, files with no build tags at all compile everywhere. That's where your shared code lives. This composes beautifully with cross-compilation. Run go build and Go picks the files matching your current platform. Run GOS equals Windows GOARCH equals AMD 64 go build, and it selects the Windows files instead, from the same source tree on the same machine. This is how the standard library itself handles platform differences. The OS and net packages are full of tagged files. Build tags aren't limited to platforms. You can define your own. The classic example is debug versus release builds. One file tag debug defines debug mode as true and a debug log function that prints. A second file tagged debug, not debug, defines debug mode as false and a debug log that does nothing. A plain Go build selects the not debug file. Your release binary contains no debug code at all. Smaller binary, no performance cost, and no debug endpoints leaking into production. Go build tags debug flips the selection and gives you the verbose build. The critical practice here: always provide the negated fallback file. If you only write the debug file, a default build fails to compile because debug log doesn't exist. Every custom tag needs both sides. The same mechanism separates test suites. Tag your integration tests with // go build integration tests that need a database or an external API. A plain Go test runs only the fast unit tests. Go test tags integration runs the full suite. Your CI can run unit tests on every commit and integration tests nightly, with no test framework configuration, just the compiler. Go 1.16 introduced the embed package, a way to include files in your compiled binary at build time. You write // go embed help.txt directly above a variable declaration, and the compiler reads that file and bakes its contents into the executable. At runtime, the variable just holds the data, no file I/O, no path resolution, no missing file errors. The variable's type decides the form. Declare it as string for text files, configuration, templates, help text. Declare it as byte for binary data, images, fonts, anything raw. And note the blank import. Import embed is required to activate the directive when you're only using string or byte slice embedding. Why does this matter? Deployment becomes copying one file. Your assets can't drift out of sync with your code because they're versioned and compiled together. And it works on read-only file systems in minimal containers anywhere the binary runs. The constraints to remember: the embedded files must exist at compile time, paths are relative to the package directory and can't reach outside the module, and the embedded data is read-only. You can't modify it at runtime. For more than a file or two, embed an entire directory tree with the embed.fs type / go. Embed templates / above a variable of type embed.fs pulls in every file under templates, preserving the directory structure and the original paths. Embed.fs implements the standard fs.fs interface, and that's what makes it powerful. Anything in the ecosystem that accepts a file system accepts your embedded files. fs.walkdir to traverse them. Read file to load one by path. HTML/templates parse fs. net/https file server. The embedded tree is a drop-in replacement for a real directory. One directive can take multiple patterns, templates/html/ and templates/css/ on the same line, or you can list individual files. The paths you use to read a file are the same paths you embedded, templates/index.html, exactly as it appears on disk. Keep binary size in mind. Every embedded byte lands in the executable. Small assets, templates, style sheets, a few icons, embed freely. Hundreds of megabytes of video, keep those external. Let's look at the 3 patterns you'll actually use. First, the embedded web server. Wrap your embedded file system in http.fs and hand it to http.fileserver. Your entire static frontend is now served from inside the binary. Combine it with template.parsefs for server-rendered pages. The result is a web application that deploys as a single file. No assets directory, no Docker copy steps, no path configuration. Second, SQL migrations. Embed your migrations directory, and at startup the application reads each .SQL file from the embedded file system and applies it in order. Your schema changes ship inside the same artifact as the code that depends on them. They can never be out of sync, and they work in containers with no volume mounts. Third, default configuration and reference data. Embed a config.json with sane defaults, or a CSV of country codes, and your program works out of the box with 0 external files. One practical tip: keep your embedded assets organized under a dedicated directory, and remember that embed directives respect build tags. You can embed different assets for different build configurations. Now the third feature, Workspace mode, added in Go 1.18. It solves a specific, painful problem, working on multiple modules at the same time. Before Workspaces, if Module A imported Module B and you wanted to test a local change to B, you had 2 bad options. Publish B somewhere and update A's go.mod, or add a replace directive pointing at the local path, which you then had to remember to remove before committing. Everyone who did multi-module development has accidentally committed a replace directive. Workspace mode fixes this with one file. Run go work init /module A /module B, and Go creates a go.work file listing the modules in your workspace. From then on, any import of Module B from Module A resolves to your local copy. The workspace takes precedence over published versions. No replace directives. No edits to any go.mod. No publishing. The go.work file itself is minimal. A Go version and a use block listing module directories. You can write it by hand, and you can include modules outside the workspace directory with relative paths. The day-to-day workflow is what makes workspaces valuable. Edit code in Module B, switch to Module A, run Go test. The change is already visible. No commit, no push, no version bump. The iteration loop across modules becomes as fast as within one module. The commands, Go work init creates the workspace. Go work use adds a module, and go work use r removes one. Go work sync pushes the workspace's dependency resolution back into each module's go.mod, which you run before releasing. The natural home for workspaces is the monorepo. Several services, a couple of shared libraries, one go.work tying them together. Every service sees library changes instantly. It's equally good for library development. Keep the library and an example app in one workspace so your examples never rot. 2 best practices. First, workspaces are a development tool, not a production mechanism. Your CI and release builds should work from each module's go.mod alone, so don't let correctness depend on go.work. Second, keep the workspace focused, related modules only. Whether to commit go.work is a team choice. Commit it for a monorepo everyone shares. Git ignore it when it's your personal setup. Build tags // go. Build comments select which files compile, by OS, architecture, Go version, or custom tags like debug and integration. Activated with tags. Always provide the negated fallback so every configuration builds. Embedding // go. Embed bakes files into the binary. String for text, byte slice for binary data, embed.fs for whole directory trees that plug into net/http and html/template. Workspace mode. Go work init creates a go.work file so multiple local modules resolve against each other. No replace directives, no publishing. Development only. Production builds rely on go.mod. Next episode, advanced patterns, dependency injection, middleware chains, and plugin architectures. The episode where Go's simple pieces compose into real application architecture. This course is based on the complete guide to Go programming, available on Apple Books and Amazon. Find it at pixelstech.net/book. See you in episode 25.